Hello everyone, in this video we are going to solve this equation using double angle formulas. Double angle formulas in trigonometry are formulas that we can use to rewrite expressions that have a double angle. For example, if I have the sine of 2u, that means I have the sine of twice the angle u. And we can rewrite this as an expression with a single angle u by using these conversions. We have sine, cosine, and tangent. Notice that the cosine of 2u has three different ways of being rewritten. That's because the general form here, cosine squared minus sine squared, I can change sine squared into 1 minus cosine squared and then collect the like terms and simplify the expression, and that's how you get this expression here. We can instead change cosine squared to 1 minus sine squared and combine the sine squared together, and you'll end up with 2 sine squares here. So you can play around with that. But for now, we're going to use the double angle formula for the sine so that we can solve this equation. Okay, so when we want to solve equations, we usually look at the expression and see if we can use any identity that we know of. If we want to factor, anything we can do that we would do algebraically, see if we can do it with this expression. And I notice that I have a cosine and a sine. So they're not like terms. I can't combine them together. There's nothing here to factor. I do notice that I have a sine of a double angle, and that should um, tell us that we should use one of the double angle formulas to simplify it a little bit. And then maybe I'll end up with like terms that I can combine and then figure out and solve this formula, this equation, I'm sorry. So let's start. I see that the sine of 2x I can rewrite as this expression here. So I'm going to go ahead and do that. I'm going to say 2 cosine x, keep that for now. And then for the sine of the double angle, I'm going to write 2 sine of the angle, cosine of the angle. So it's going to be 2 sine of the angle, and in this case my angle is x, times the cosine of the angle, which is also x, equals 0. So the only thing I've done here is my first step is I took sine of 2x and I rewrote it using the double angle formula as 2 sine x cosine x, like it says here. Okay, so let's continue. Now that I have this expression, I see that I still have sine, I have cosine and cosine, but I notice that between terms number 1 and term number 2, they both share something in common. I see that these two terms both have cosine x and cosine x. So that tells me that I can factor out this common term of cosine x. So I'm going to take cosine x and cosine x, and I'm going to bring it outside of the parentheses. I'm also going to take the 2 outside the parentheses because both terms also have a 2. So to make this easier to visualize, I'm going to write this as products. So I'm going to take 2 cosine x, I'm going to write it as 2 times the cosine of x plus 2 times sine x times cosine x equals 0. I'm going to underline everything that these two terms share. So I have a 2 in this term and I have a 2 in this term. I also have a cosine x in this term and a cosine x in this term. Everything I underlined, that's what's going to come outside the parentheses. So 2 comes out and cosine x comes out. Once I bring those out, I can go ahead and remove those common terms. Now I open my parentheses, and what I have not removed here in this case, I've removed both the 2 and the cosine x. That means I'm left with a factor of 1 plus, and then in this second term, I've removed everything except the sine, so sine x is left, and that equals 0. It's very important that when we factor in this manner, we go back and check and make sure that our factoring is correct. So we use the distributive property and we take this outside term, we multiply it by the first term, and we make sure that we get back our original term. So if I multiply 2 cosine x times 1, I can see that I get back the original term, which was 2 cosine x. So let me just write this here, 2 cosine x. And if I multiply that outside term by the second term, I get plus 2 cosine x times the sine of x, which is the second term that I had in my expression originally. Yes, these are switched. I used to have sine x, cosine x, but remember that multiplication is commutative. Cosine x times sine x is the same thing as sine x times cosine x. Like 5 times 4 is exactly the same as 4 times 5. So this is equivalent. This that I wrote in green, this is something you do in your head. You look at it, you check it in your head. You don't have to write it out. If you must write it out, go ahead and do that. But it's not necessary. Once you check that this gives you exactly the same thing you had originally, that means that it's factored perfectly. Let's move on. Now I can see that I have the zero product property. If something times another thing is equal to 0, then it must be that this term here, 2 cosine x, is 0. So I can write that 2 cosine x equals 0, or 1 plus sine x is 0, or both are 0. Now I can solve for x. I'm going to isolate cosine x by dividing by 2 on both sides. Cosine x equals 0. And now I find the values for x. X, remember, is the angle. We're finding what is the angle whose cosine is equal to 0. So it might help you to have a unit circle around, or you can just sketch roughly where this angle might be, such that when I take the cosine of it, I get 0. So I know from the unit circle that the cosine of pi halves is 0, and I also know that the cosine of 3 pi halves is 0, and nowhere else on the unit circle is this true. I do also know that in one turn of the circle, I have 2 solutions, pi halves and 3 pi halves. But if I go around again, I find coterminal angles that will give me, again, the same solution. So I will hit these solutions infinitely as I go around infinitely around the unit circle. Same thing happens if I go counterclockwise. Therefore, my answer is x is equal to pi halves, and x is equal to 3 pi halves, and then I add and subtract n revolutions around the unit circle of 2 pi, because 1 revolution is 2 pi. And I also do the same for this one, n revolutions of 2 pi, plus minus, where n is an integer. For my second factor here, I'm going to isolate sine of x by subtracting 1 from each side, minus 1, minus 1. And that gives me that the sine of x is equal to negative 1. So again, I'm going to find that angle whose sine is negative 1. When I look at this sketch here, I know that the sine is going to be negative 1 only at 3 pi halves. That's the only place where the sine value is equal to -1. Remember the coordinates at 3 pi halves. Sine is -1. Nowhere else does this happen. So another solution that I find for x, here I have the previous two solutions. I also have another solution at the same spot that I had found before for cosine equaling 0. So x is equal to 3 pi halves plus minus 2n pi, because I will hit the solution every time I go around the circle 2 pi. Okay, now that I have all three solutions, here's one, here's the other one, and here's the other one, I can also write a condensed form of this solution, because I notice that the three solutions that I have, one which is a repeated solution that I had already found, I can also hit these solutions if I go around pi lengths instead of 2 pi lengths. I will hit each one of the solutions. So I can go around every pi and I will find the solution to this equation. So I can write this condensed solution as the following. I can write x is equal to pi halves plus minus n pi. And this solution will take care of all these solutions that I had written before. So there you have two possible ways of stating your solution. You can write it like this, or you can just say that this is your solution. These two x values. I don't include this one because this one is already here. So I'm not going to write a solution twice, the same solution. Okay? If you need to go back, hit rewind, replay, skip to the parts where you don't understand, have fun with it. I'll see you in the next video.